In this video, we're going to look at using the 5-step method to predict what reactions will occur in an electrochemical cell, as well as predicting cell potential and empirical observations in the operation of a voltaic and an electrolytic cell. So we're going to start with this voltaic cell. We know it's a voltaic cell because of this voltmeter shown in the diagram. We're going to start by listing all of the species that are present to determine what reactions will take place and identify the anode and cathode. So looking at our half cell on the left, we have a solid copper electrode. So we have copper solid present. We have a copper 2+ solution with nitrate as our anion. If we start moving from left to right, in our salt bridge we have potassium ions and nitrate ions. We've already listed nitrate, so we can just add potassium ions here. And then in our second half cell we have silver nitrate, so silver plus ions, and a solid silver electrode. Because our entire cell is made up of aqueous solutions, we also have water present. So we've listed all of our species. Next up, we're going to identify our oxidizing agents, which I'm going to underline in blue, and our reducing agents, which I'm going to underline in green. And we're going to use the table on page 7 to identify our oxidizing agents and our reducing agents. So, copper solid is a reducing agent. Most solid metals are reducing agents. Copper 2+ is an oxidizing agent. Most metal ions are oxidizing agent. Nitrate is neither an oxidizing agent nor a reducing agent. Nitrate is only reactive when it's combined with acid. Potassium ions are oxidizing agents, as are silver ions. Solid silver is a reducing agent, and water is both an oxidizing agent and a reducing agent. So we are going to identify our strongest oxidizing agent from the list that we have. So we're going to compare the strengths of copper 2+, potassium+, silver+, and water. And we're going to just look for the species on our table that is closest to the top left corner. So our strongest oxidizing agent is silver plus ions. We also need to identify our strongest reducing agent. Our strongest reducing agent will be closest to the bottom right on the table, and that's going to be solid copper. So with that in mind, we can always remember the memory device red cat and NOx. So this means that at the anode there is oxidation, and that's where our reducing agent is going to react. Red cat means that at the cathode there is reduction, and that's where the oxidizing agent will react. So looking at our cell here, we see that copper is in the left half cell, and we said that copper was our SOA. So this copper electrode is, our SRA, so this copper electrode is our anode. We see that silver is in the half cell on the right, and our silver ions are present here, making solid silver our cathode. So the cathode is not directly involved in the reaction here, it's just a conduit for electrons. So the half reaction that will occur at our anode is the oxidation of solid copper to produce copper 2+ ions. And the half reaction that will occur at our cathode is the reduction of silver ions. We can find our cell potential by finding the difference between these two. So the E0 value for this copper reaction is positive 0.34 volts, and the E naught value for the silver reaction is positive 0.80 volts. So E cell is equal to the E naught value of our strongest oxidizing agent minus the E naught value of the strongest reducing agent. So our strongest oxidizing agent is silver, so 0.80 volts, minus copper, which is 0.34 volts, giving us a difference of 0.46 volts for this battery. And then lastly, we can predict some observations and label this cell diagram. So because copper is our anode and oxidation will occur here, electrons will leave the anode, travel through the wire to the cathode. In order to complete the circuit, anions must move towards the anode through our salt bridge, and cations must move towards the cathode through our salt bridge, so that we have balance of charge and a continual loop of negative charge flow. In terms of observations, in our copper half cell, we are oxidizing copper. And so our copper electrode is going to decrease in mass as it is oxidized. The solution here will be blue because copper 2 plus is blue, and because we're producing copper 2 plus, the solution color will get darker. In our other half cell, we are taking silver ions and plating to form solid silver. And so there's going to be an increase in mass at our cathode as solid copper is plated, or solid silver is plated. Because silver is a colorless ion, we won't really see any change in color in this half cell. And we'll be able to confirm this reaction by using our voltmeter at the top. Our next example is a slightly different type of cell. We haven't looked at this yet, but this is an electrolytic cell. So electrolytic means that we have to supply power to make the reaction go. We can still use the same 5-step method, though, to predict what will happen in the cell and what observations we might see. So we're going to start by listing all of the species we have present. You'll see that our electrodes are inert, so we don't have to list them among the species. And we'll see that we have liquids here instead of aqueous. That means that there is no water present, so we just have a molten ionic compound. So our species present is potassium ions in their liquid form and hydroxide ions in their liquid form. We are going to assume that the liquid form will undergo the same reaction as the aqueous form. This may not be true in reality, but for our purposes, at the level we are, this is a fair assumption. So we can still use our table to assign RA and OA. So I'm going to assign oxidizing agents with blue. And the only oxidizing agent present is potassium. And then I'm going to assign reducing agents in yellow, and the only reducing agent present is hydroxide. So that makes this a little bit easier for us to determine what's going to happen in this reaction. So our strongest oxidizing agent then must be potassium, and the reaction that's going to take place with that is the reduction of potassium when 1 electron is gained to form solid potassium. For our oxidation reaction, we're going to have 4 hydroxide ions oxidized to form oxygen gas, water. Since this is molten, likely that water is also going to be a gas, and electrons. So I've just listed water as a gas because it is very hot. Molten ionic compounds will be hot. So that's my 2 half reactions. I can write my E values for each one. So the E naught value for the reduction of potassium is negative 2.93 volts. Potassium, not a great oxidizing agent. And the E naught value for The oxidation of hydroxide is positive 0.40 volts. So this is going to be a little bit different than what we've seen in the past, where my E cell value is actually going to be negative. So I'm going to take the strongest oxidizing agent value and subtract the strongest reducing agent value. So I'll have negative 2.93 volts minus 0.40 volts, giving me a cell potential of negative 3.33 volts. When we talk about electrolytic cells, we'll talk more about this, but this is the voltage that's required for that power supply to overcome and cause this reaction to occur. Okay, so the last thing that we're going to do is identify what reactions we might actually see in this cell. Since they're both inert, we're just going to arbitrarily call the left our anode and the right our cathode. So electrons will leave our anode and enter our cathode. Anions will go this way, which makes sense as we have hydroxide reacting at the anode, and cations will move this way, which makes sense as we have potassium reacting at the cathode. And so now we're going to look at what we'll actually see happening. So we're going to have potassium solid forming at our cathode. And so we're going to have plating of potassium at the cathode. That's going to cause an increase in mass of our cathode. At our anode, we're producing gas. And so what we're going to see in our molten solution is bubbles. And those bubbles are the result of the gas being produced. Because we're not producing a solid or using up our electrode, there's not going to be a change in mass of the anode. And so even though this is a new type of cell to us, by using the same 5-step method, we're still able to identify what will happen in the cell and label any observations we may see accordingly.